This is Lab 4 for Physics 1. The purpose of this lab was to use Newton's second law to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. The result was that the energy principle was satisfied, and my data matched the model best when the y positions were used to find the period rather than the x positions. In order to get these results, I put the video given to us into Tracker. Just like in previous labs, I set the length scale to 0.70 meters by using the distance from the attachment point to the center of mass at rest. I chose the coordinate system so that the origin was at the attachment point and the y-axis was aligned with the spring. I wanted to start my analysis when the motion starts, so I started from the video frame in which the mass was just about to be released from rest, which was frame 6. I identified the object's position in the video by continually marking the center of mass of the object in every single time frame. Doing this gave me the data you see right here. So because you have x positions and y positions due to the way the spring is moving, there will be two graphs, these right here. We will have a t versus x and a t versus y using the x or y position points respectively. Now in order to set up my model, I needed some information from the experiment. As seen from the chart, the initial position is this right here. And since we know the mass was released from rest, we know the initial velocity is 0 meters per second. The mass of the object was 0.402 kilograms. Now we needed information to specify the interactions of our model. For the wave force, we will need gravity is equal to 9.8 meters per second squared, which is the strength of the gravitational field. For the spring force, we will need K, the spring stiffness, and the relaxed length of the spring, L naught. To get these quantities from the video observations, we had to perform several calculations. However, because the spring is moving up and down, but also from left to right, we needed to find T, K, and L naught in the x and y directions. So we did T versus y first. The very first thing we did was change the graph in Tracker to be T versus y. We found T, which was the period of oscillation for a spring mass system whose formula you can see right here. If we rewrite this equation, we see we can solve for an unknown spring stiffness if we know the mass and period oscillation, which again is T, by using this formula right here. We used our data to get the period. The period is just the time interval for one complete oscillation, so I measured the time interval for 3 oscillations by starting at release and then looking at 3 oscillations later when the mass is again at the lowest point in the oscillation. So as you can see here, 3t equals t final minus t initial, which gave t in the y direction to be equal to 1.492 seconds. Plugging this in, we estimate the spring constant in the y direction, ky, to be 6.8357 newtons per meter. Now we can use the observation of static equilibrium to find the relaxed length of the spring. We do this by using the equation you see here and following the steps you see here as well. We find that the relaxed length in the y direction is 0.12367 meters. In order to find t versus x, we use the exact same formulas, only we need to change the graph in Tracker to show t versus x in order to get the tx. Now we can go on to make changes to our code. I decided to make 2 separate codes, one with t versus y and t versus x. So let's look at the t versus y first. I changed the initial conditions and system properties to what you see here, which we were given and found earlier. Then I changed the K and L naught to what we computed earlier using the Y positions, as you can see here. I then proceeded to change the code to specify the spring force vector. L gives you the length and orientation of the spring. The L vector points from the attachment point to the location of the mass. The spring attachment point is given by spring.pos. Next we ended the while loop where we use Newton's second law in order to predict the motion to what you see here. By doing this, I got the model that you see here, or we'll see here in 2 seconds. This is the t versus y positioning of the code. The red ball is the actual model while the blue ball is my data. You can see how they match extremely closely, just being slightly off as the red ball moves slightly faster. In order to create the model of the t versus x positions, you do the exact same thing you did for the t versus y, only changing the t, k, and L naught to the values you found them to be using the x positions as found earlier. Doing this gives you the model that you see here, with again the red ball being the model and the blue being my own data. Initially, my data seems to follow the models closely. However, as time goes on, they get further and further apart to the point where they are moving in opposite directions at the end. So in conclusion, my y-graph data is a much better and more exact predictor of the model data. Now back to the PowerPoint. Now we can go ahead and plot our energy graph. We used Newton's second law for the part above, but now we are using the energy principle. So since we are choosing our system to be the spring, the mass, and the earth, the change in the total system energy, delta E, is equal to the sum of the energy changes inside the system, delta K, plus the change in gravitational potential energy, delta UG, plus the change in spring potential energy, delta US. And this all equals 0 because there are no interactions that transfer energy to and from the surroundings if we neglect small effects like air resistance. So, to compute these energy changes in our code, we had to make a couple changes. You can see K, UG, and US computed at each iteration right here. Now once we enter the while loop, we see the energies are defined right away using these 3 lines of code. So they are defined here and they're used here. These 3 lines are important because we want to be sure to save the initial energies before we make any new motion prediction using Newton's second law. Now we need to compute the final energy changes, so we did that using this code right here. When you run the code, you get this energy graph. The change in kinetic energy is the blue line, the change in spring potential energy is red, the change in gravitational potential energy is green, and the change in total system energy is the yellow line. We can see that the energy changes also oscillate. The changes in both the gravitational potential energy and the spring potential energy oscillate with the same period as the position of the mass changes. These energy changes are also roughly the same size, but are opposite in phase, meaning when gravitational potential energy increases, the spring potential energy decreases, and vice versa. The changes in the kinetic energy are also both positive and negative. The mass gains and loses kinetic energy, with the kinetic energy change oscillating twice as fast as the potential energy changes. As you can see from the graph, delta E is 0, just as we expected based on the energy principle. So that actually answers our first what does it mean? Yes, the energy principle was satisfied, with the reasons being as I explained a little earlier. As for the second what does it mean, I answered it earlier as well, when I was showing and explaining to my calculations in my two models with the t versus x and t versus y, estimating my period of oscillation from the x position data and then y position data.